Hello and welcome to the first Oxford University Innovation Online Special, The Future of Energy Generation. I'll be your host for the next hour, OUI's Comms Manager, Gregg Brown. This is a pilot episode for a new series we're considering, where we'll be going from sector to sector, looking at breakthrough technologies emerging from Oxford University and the companies it helps create. There will be a live chat open during this broadcast with people from OUI here available to speak with you. Also, we're always on the lookout for new talent and collaborators who can help grow our companies and ecosystem. If this sounds like you, a link on how you can get involved will be down in the description. Also, if you enjoy this content, a like and a subscribe is always appreciated. On today's broadcast, we will be speaking with Gregg, the CEO of ODQA Renewable Energy Technologies, a company which is looking to harness the heat of the sun as a fuel source. We'll also be speaking with Chris Case of Oxford PV, which is a company developing the next generation in solar technologies. But first, here's a professor of economic policy at the University of Oxford and one of the UK's foremost thinkers on the climate crisis. We wanted to invite Professor Sir Dieter Helm here today as we will be discussing technologies which could have an impact on the climate crisis. I wanted to get his take on the importance of innovation. Over to you, Dieter.
There can be little doubt that the fight against climate change, one of the great challenges of our time, is not going well. Every single year since 1990, we've added 2 parts per million to the carbon concentration in the atmosphere. And last year, in the great lockdowns, emissions fell, but we added 2 parts per million concentration of carbon to the atmosphere. And it is that carbon concentration in the atmosphere that matters. So, despite all the hullabaloo about COP26 and all the great speeches, we have to stand back and say, do we really have the wherewithal to tackle climate change, or do we need something more? And that's where innovation becomes absolutely central. It's true that existing technologies can do quite a lot, and getting rid of some of the existing technologies like coal can make a big difference, though there are big setbacks in that programme now, given what's happened in the gas markets before the Russian invasion of Ukraine, and now reinforced by that invasion. There always will be enough fossil fuels to meet demand. We've got enough oil, gas and coal in the Earth's crust to fry the planet many times over, and the short-term problems in the gas markets, etc., will be exactly what they are, short-term problems. But then we're back to the hard graft, dealing with climate change and designing an energy system capable of switching from an economy, a world economy that's 80% dependent on fossil fuels. The rest is largely nuclear and hydro, to a world in which fossil fuels play a relatively small part, and those fossil fuels that do play that part are sequestrated, the carbon emissions are sequestrated from them. So anyone doubts that innovation matters is on another planet. It really does, and if innovation doesn't deliver, we won't deliver. So the good news is that if you look across the energy full supply chain, full industrial chain from the generation right through to the household and supply, there's innovation going on all over the place. There's a cornucopia of opportunities, and it's no surprise that it's universities that are on the cutting edge of this. After all, in a way, that's what universities are for, trying out new ideas, coming up with new ideas, and then it's for industry and the wider markets to sort out the wheat from the chaff and work out which ideas are going to work and which ones aren't. And what's comparatively new, certainly over my career, is that the taking of ideas and putting them into practice has now become an intimate relationship between investors, businesses, and universities. And that's overwhelmingly a good thing. There are some risks, of course. Pure research doesn't get the kudos and support that it needs, and that there is a rush for near-market solutions, and we don't keep to the university rule book in the sense of the pursuit of knowledge and excellence. So let me take you through a little canter of what's out there and what will need to be done in order to get us onto a path where we might actually start delivering climate change mitigation. And generation's obviously the big ticket. And the first thing to say is there is no shortage of energy. Okay, the sun comes up every day. It's a giant fusion nuclear reactor, and it provides sufficient energy for all our needs and many, many more on top. It's said that an hour's sunshine is equal to the world's electricity consumption for a year, but you know whether that's correct or not, you get the message. We've got tons of energy. Okay, we've got past solar energy embedded in the Earth's crust, oil, gas, and coal in superabundance, and we've been taking that geological solar energy and putting it back in the energy. That's why the greenhouse effect is giving us the problems that we've got. And we've got lots of other indirect ways of capturing that solar energy, in particular through wind, as well as also the conventional solar panels and so on. So if we are to knock out our reliance on coal, which is still the big generator of electricity out there in the world and expanding in China, India and sub-Saharan Africa substantially, we need something else. And we know that wind technologies, solar panels, etc. can contribute. But I don't really think that anyone believes that you can power a modern industrial economy on current wind and current solar technologies alone. Of course, they're very important. Of course, they're going to expand. And of course, there's enormous technical change, particularly in the solar bit. Much of the wind technical change has kind of happened, and the size limits have been reached. And the materials, of course, very carbon intensive in wind farms, but there's stuff to be done on those. But basically, wind is a low density, disaggregated, intermittent technology. And most of the interesting stuff around wind is about how to deal with that intermittency, and in particular, next decade or so, the heavy reliance on gas that will entail. Solar's different. There are all sorts of ideas for new materials, harnessing new ideas to create better ways of capturing that solar energy up front. And that's a research task. Oxford's very good at that stuff, and it's going to have to produce breakthroughs. And not just at the level of the panel and the materials. The transmission over very long distances of solar is important, and clearly attempts to produce large-scale power from large-scale solar plants are going to come into the picture as well. And it'll be important for backing up desalination, which will be needed for many of the cities around the world as the temperature inevitably hots up around the world. So that's in the kind of what I call the conventional renewables box, and the ancillary issues around them, how to manage intermittency, cables, networks, all that kind of stuff. And in every one of those areas, there's massive scope for innovation. Indeed, it's going on. And that's the good news. So then we look at other forms of generation. It's not that long ago where people thought that, certainly in energy policy circles, nuclear power was a thing of the past. The argument was that in Western democracies, populations would no longer stand being located anywhere near a nuclear power station, in part because they completely misunderstood the risks compared with other forms of energy generation. There was a concern about the links between civil nuclear and military, and a deep concern about the waste and the legacy left to the next generations. And those problems have been with us for a long time, but on top of those is layered cost. And certainly in Europe, it's turned out to be very expensive to build the small number of nuclear reactors that are currently under construction within Western Europe in particular. So what about nuclear going forward? Well, innovation matters here a lot, but it's innovation about costs as well as the technology itself. There's no reason why you can't develop small reactors as alongside large reactors, although there are some science and some economics about why large reactors tend to be more efficient than small. There's no reason why you can't innovate in production technologies and get much more of the nuclear plant built in factories on a modular basis. And there's no reason why one can't do a lot with supply chains to get the costs of the standard PWRs down. After all, France built over 50 of them, and I think in 1 year was building 6 of them simultaneously. So it's not as if we have to build one at a time. A lot can be done to improve those processes. And there are ambitious plans out there. Macron, if he wins the election in France, has suggested he's going to build another 6 reactors. It's not inconceivable that we might say, well, why aren't we building 6 reactors in the UK? Why don't we build 12 reactors together with the French? More difficult in this post-Brexit world, but there's all sorts of international cooperation that's possible. I'm not advocating we do that. I'm simply saying it's one of the options on the table. But then you need to move on. And there's a huge amount of excitement about fusion and what some call the star builders. People working out not only how to do fusion, but much more importantly, how to harness that in a way that can deliver continuous electricity supplies and net energy gain into the long run. Oxford's always had a nuclear capability. It's part of science and the core of science, and Culham and elsewhere have been deeply involved in developing all sorts of aspects of nuclear power, but fusion looks to be at least exciting at the moment, and the private sector is beginning to come on board. Now, there's hydrogen, which is really a storage technology, which may be absolutely critical to future industrial structures. The hydrogen process itself, pretty well known. The options are convert natural gas to hydrogen, convert renewable energy to hydrogen, and then think of a way of storing it. Green ammonia is an obvious play, and again, Oxford's full of people working on green ammonia, including my colleagues in New College. That's got to be a big part of the story, both from an industrial perspective, but also, I come on to in a moment, the heating issues, households and buildings and so on, and our deep reliance currently on natural gas in that world. So hydrogen's part of the play. If it's from natural gas, and I suspect it will be for some time, you need CCS. You need to be able to store that carbon offshore, and onshore indeed, in depositories. In other words, having taken the carbon out of the ground with the fossil fuels, put it back. And if we really can put it back, and at scale, then that begins to question the assumption that we're just going to get out of fossil fuels, and ask the question about how fossil fuels might be used in a much less carbon-intensive way. No judgment on my part about that, but it seems to me CCS draws on geological skills geological sciences, and again, the kind of expertise that universities have. So that's part of the frame too. And then beyond that, loads of other stuff. Who knows? Going on in labs, scientists thinking through sometimes wacky ideas, but who's to say that we have to live in a world of 3 fossil fuels and 2 renewables and nuclear power into the future? Who knows what the future lies out there? All that one can say is that the rate of return on R&D is phenomenal. So then you go down the chain. I mentioned the networks, long distance connections for solar, long distance for geothermal, long distance from remote networks of disaggregated, decentralized nuclear and in particular technologies for disaggregated wind, in particular offshore wind. The networks and the cabling have received remarkably little innovation for a very long time. I don't know if they're still there, but there were recently still oil-filled cables in London from the 19th century. This area cries out for innovation, for smarter systems, and with them the integration of IT and smart AI, big data, machine learning, all of those technologies to come to play. And all of this is for us at the end of the path. We, you and me, are ultimately the polluters. We buy the stuff that has the carbon embedded in it. And if we look at what we do at the household level, there is, again, massive scope for innovation. We use energy very inefficiently. It's not necessarily the case we want to conserve it. Energy goes from one form to another, but we use it very inefficiently. The housing stock needs addressing. Clearly, the domestic heating needs addressing. And then, of course, there's the whole paraphernalia associated with electric charging in decentralized energy networks. So I hope that very eclectic canter through all the areas, or some of the areas where innovation may be forthcoming, gives you a sense of how both necessary this is if we're going to crack climate change, and that's what really motivates many academics and many students, but also how exciting it is in terms of what may actually be coming down the track. And who knows, in 2050, when all our net zero targets come to fruition, there may be a very different energy world for you, for my students as they are now, and for the next generation. Let's hope so. Thank you very much.
Professor Sir Dieter Helm, thank you very much. Now, the university and its companies are currently exploring new technologies which could be used as fuel for the future. An example of this is Oxford Green Innotech, which is seeing whether we can use ammonia waste and transform it into hydrogen fuel, which could be used to provide clean energy. Another is Mixergy, which is developing smart water tanks, currently making their way to UK homes as we speak. But the Holy Grail has always been harnessing the power of the sun. Already powering the natural world for billions of years, many innovators have looked for inspiration to the sun to solve our current energy crises. On the far end of the scale, this includes the Dyson sphere, a hypothetical megastructure to be built around a star, where you would take energy directly from the source. We may not be there yet, but we have technologies which are coming on at pace, which could definitely help. Home to the Culham Centre for Fusion Energy, Oxfordshire has become a global hub for fusion energy. If we crack fusion energy, it could provide a near limitless source of clean energy for humankind, which could be transformative the world over. The university is also involved in this pursuit of fusion energy through its company, First Light Fusion. The company, which has recently raised $45 million in its Series C, is yet to prove game, but it is rapidly expanding its team and its research into fusion energy. Should it prove successful, it could be a game changer worldwide. In the meantime, other Oxford companies are looking at how we can take energy from the sun. ODQA Renewable Energy Technologies is one such company. ODQA is looking into whether it can use heat from the sun as a fuel source. I recently sat down with Gregg, the CEO of ODQA, to discuss.
I'm joined by Gregg, the CEO of ODQA. Thank you very much for joining me today, Gregg.
Thank you, Greg, for having me.
Right. ODQA's tagline is "We decarbonize heat." But what exactly is ODQA doing with heat?
So, as you would probably know, half of what we use as humankind as energy, it is consumed as in the form of heat, and currently we burn something to get that heat. And ODQA's idea is we should instead use sun because it is abundant, and we can produce any grade of heat from it.
Excellent. So where do you see the applications of this heat?
So that there are numerous applications. The most prominent one is industrial process heat. For example, to produce any kind of metal, or to produce cement, or to produce some other materials, you need to have lots of heat to process those. Category is electricity generation. Since heat is much simpler, cheaper to store, you can generate heat and you can use that heat during when the sun is not shining or the wind is not blowing. This is the second category. And the third category, the most exciting one, is to produce hydrogen from it, and therefore to produce other solar fuels, to store the sun's energy in the form of chemical bonds, if you will.
So by using the solar cells and the hydrogen cells, is how you effectively transport and utilize the heat?
Yeah, so in traditional PV cells, you have semiconductors to generate electricity. In our technology, instead of PV panels, we use mirrors to concentrate the sun's rays to a focal point. At that focal point, we generate heat and we store that heat. By doing this, we can use 60% of incoming sun's energy, whereas in PV panels, you can just incoming energy. And this is one of the advantages of concentrated solar energy.
So what would be the environmental impact of industry, broadly speaking, switching over to ODQA's heat sources?
So currently, for example, our first application is industrial rotary dryers. And as we speak, there are no renewable solutions for that. The only semi-renewable solution is electrified rotary dryers, but they use grid electricity, which is carbon contaminated. So when you are using electricity from grid, you inherently producing carbon. So our solution is decarbonized. Our first product will be a hybrid solution. So it will be only used when the sun is shining. But the next generation of our product will be fully decarbonized. So we will be using sun's energy to produce heat, and this heat will be directly used in industrial processes.
Excellent. So could you talk me through a little bit about the origins of ODQA and what its link to the university has been, and what support you've received from the university and the wider ecosystem in your journey?
So with pleasure. So in 2016, I came to Oxford to do my MBA. And while doing my MBA, I had to complete an entrepreneurship project. And I thought, since I'm in Oxford, and since Oxford is, every department of Oxford is top 10 in the world, I thought to myself, let's connect to world-class scientists, and let's try to have a real company out of this entrepreneurship project. And I reach out to Professor Peter Ireland, who is the head of Oxford Thermofluids Institute, the largest engineering institute in Oxford. And I told him, Professor, you have world-class knowledge base in jet engine development, heat transfer, and all the related phenomena around it, aerospace. And I proposed to him, would you like to use this expertise in renewable energy? And he was very interested, and he asked Oxford University Innovation to look into our concept, and they helped us immensely. And we started the patenting procedure of our idea, and then they introduced us to Oxford Sciences Innovation. At that time, then they changed their name into Oxford Sciences, Oxford Science Enterprises. Right after I finished my MBA, we received an investment offer from Oxford Sciences, and that was the start of our journey. And quite frankly, Oxford ecosystem is extremely good and vibrant, and there are lots of capital in the city. And I need to note that Ox Sciences is the world's largest university-based venture capital company, and that's enabled lots of spin-outs. And with the help of OUI, we are in this era of company startup. It is the fastest startup generating era, I guess, in Oxford's history.
That's correct. We had 31 new companies in the calendar year just gone, and I think the year that ODQA came around, we hit 24. So we are seeing an increase over time in the amount of companies that we can generate, and Ox Sciences has definitely been a catalyst for that effort. When I first encountered ODQA, actually, so this would have been 2017, 2018, around that sort of time. You were starting to look at geothermal applications of the technology from Peter. And when I've recently interacted with you guys, I've seen you've done this fascinating pivot into kind of using the mirrors to harness the heat from the sun and focus it into that one point. And I was just wondering what brought about this pivot, what the impact that pivot has had on your company's development.
So I did a double major while studying engineering. I did geological engineering and civil engineering, and geology is always very close to my heart. And at the very beginning, let's use Earth as a very large heat source, because wherever you go, you can dig 20 kilometers and you can get industry grade heat anywhere in the world. It's not geographic specific. And that was the original idea. Let's harness this energy and use it. The thing is, after a year, we looked into the concept. We looked into all the heat transfer coefficients and all the mechanisms of transferring that heat to surface. We realized actually rocks are very good insulators, and before you get the heat from the source rock, it starts to cool down. So the models show it won't be as feasible as we have hoped. And around that time, I started looking into many different application areas and identified solar source is much more accessible, and we don't have any space restrictions. And then we realized it is an untapped market, and the transferable skills fit perfectly with the market needs. and we pivoted into solar thermal.
Mm. Yeah, just as an addendum to that question, something you mentioned with geothermal is that it could be done basically anywhere. And from what I've seen of the images that you guys have provided to me, one of which will be appearing on screen, we have these fantastic towers that you're building up with this focal point at the top with all the mirrors reflecting heat back up to that. Is this technology that could be used anywhere, or is it specifically something for hotter climates?
Yeah, it is. It can be used anywhere in the world, but the economics are not the same. So if you and this is the main difference between PV panels and concentrated solar power. In concentrated solar power, the sun's rays need to come parallel to the ground all the time. So when you have a cloud cover, your output of the system decreases significantly because you have to concentrate them.
Mm.
But in a PV panel, you can use scattered sunlight. Basically, in a cloudy weather, you can use your system effectively and efficiently. So the places like the UK, where we have lots of cloud coverage, the economics of the system is not that great.
Mm.
So there is a geographical, economical basis of our system. But based on our models, our system's levelized cost of energy, levelized cost of heat, will be cheaper than burning gas. And the burning gas, as we speak, it is the cheapest form of generating heat. Therefore, we think that our system will be accessible and cheaper than carbon heavy alternatives for the majority of the world.
Excellent, thanks. And just a final question for you, Geddes. What positive impact do you see ODQA having on the world at large?
So currently, we have very small impact. We are a small company, but the technologies we are developing has the potential to bring colossal impact. Because the reason why I'm saying this is the technologies we are developing and the technologies other renewable energy companies are developing, they are terminal technologies, meaning that once we develop our technologies, they will be used not only for 10 years, not only for 50 years, not only for 200 years, but for the incoming millennium. Like next 1,000 years, we will have the sunlight, we will have the wind. So the technologies that we are developing today will have extremely big impact to the future generations, because what we are developing is the stem of what will be the standard of the next generations.
Excellent. Well, Geddes, thanks for joining us, and pleasure speaking with you.
Thank you for having me, Greg.
Thank you to Geddes for joining us there. A quick reminder, we are looking for people to come and work with us and collaborate with us here in Oxford. If that sounds like you, the link on how you can get involved is down in the description. Now, from the sun's heat to the sun's light. Oxford PV is one of our leading companies here in Oxford and is looking at how it can develop next generation solar cell technologies. At present, the current generation of solar cell technologies has a transfer rate of about 15%. Oxford PV solar cells are reporting up to about 29% conversion rate between the sunlight to energy, with a potential higher ceiling yet to come. We heard from Chris Case over at Oxford PV how the company is coming along.
So, the sun beams 470 exajoules of energy onto the Earth's surface every 88 minutes, enough to power the entire planet for a year. And you may have heard the phrase peak oil. well, you won't hear the phrase peak sun because it's got 4.5 billion years left to run. And in that time, it's never raised the price of its energy. And with the exception of an occasional eclipse, had a blackout. It's the ideal renewable energy source. And of course, we have to open with a quick reminder that we all need to address decarbonization and play a role in mitigating what is now called the climate crisis. That's the latest phrase, not climate change. And although we have topped over 1 terawatt as an industry of renewable energy in total, photovoltaics, PV, is only 3% of the mix. So even with a forecast of 50% PV in 2050, we're not moving fast enough. So this is a chart I like to use occasionally from Alliance Bernstein that overlays like a 70-year trend of fossil fuel prices. And on the right-hand side is the price of solar PV. And it's dropping. And they call it the Terrordome because it's supposed to scare an oil or gas executive and seeing what's the trend in PV prices. And if it doesn't scare them, I'm not sure what does. And the price of PV has dropped a factor of 200 in the last 40 years. Without question, solar growth is spectacular, and the investment opportunities top several $1 trillion, by the year 2050. And you can see that PV, solar PV, is much lower than any of the other forms of renewable energy, including wind and offshore wind. So even the oil companies have gotten into the game and acknowledged the role that PV is going to play in the future. And this is from Shell's Sky scenario a couple of years ago on the energy mix in the year 2050. And 50% by 2050 sounds pretty good. And maybe these guys looked at that Terrordome chart, but it's still not fast enough to stop climate change. So something you need to understand is that the solar cell is only a small part of a solar system. The cell goes into a module, and you have modules and the racks and the mounts and the land and the wires. So if you just look at the cost of the solar cell itself and reduce that, it only has a small impact on reducing the cost of the energy that's generated from that system. But raising the efficiency is a more direct benefit. So to be clear, the solar cell efficiency is, the measure of converting the sun's photons to electricity. So out of every 1,000 watts per square meter that's available on the Earth's surface, let's say a 25% efficient solar cell would generate 250 watts in that square meter. But now we have a problem. And after 65 years of continuous improvement in silicon, which is the predominant material for solar cells, they've reached their practical efficiency limit of around 25% out of a theoretical limit of 30%. So yes, the price has dropped by a factor of 200-fold, but we have a problem. We can't raise the efficiency further. Only cost reductions can be applicable. Now, and I just explained that raising the efficiency is what's required to increase the benefit from the energy. So the good news is back in 1960, two guys, Shockley and Queisser, and it's the same Shockley, by the way, who was the co-inventor on the transistor, and he gave us workarounds. And he said, you can concentrate the photons with lenses and mirrors, or you can build a concept of a multi-junction solar cell. And in this idea, you combine 2 or more solar cells, each of which absorb different parts of the solar spectrum. There's a different color in the sun spectrum. And it does mean you have to have solar cells that have different spectral sensitivities. And the most elegant way to do it is to stack them directly on top of each other. This is known as a 2-terminal configuration. And an example here, we have a silicon solar cell as the bottom solar cell, and we put on another solar cell with this material called perovskite, which absorbs in the blue part of the solar spectrum. So together, the combination actually can be more efficient than an ordinary single silicon solar cell. In fact, just combining these 2 solar cells together raises that efficiency limit from 29% to 43%. That's a big change. So let me introduce this perovskite material. So if you're, like they say on the Virgin Atlantic flights, you're in the 0.0001% of the people who've never heard the word perovskite by this point. It's an old material. It's actually a mineral that was discovered back in 1839. But all the modern applications, which date back decades, are using completely synthesized forms of this material. And the predominant application is actually high temperature superconductors. In this case, What we do is use different atoms to replace the original elements that are in the mineral perovskite. It was only discovered to be a good solar cell material about 10 years ago, and it's such a good material. You only need 35 kilograms of this perovskite. That's what it looks like in its sort of unmixed form, right? To make a megawatt of solar panels versus 7 tons of the equivalent silicon material to make the same megawatt of solar cells. So our product is really, really simple, which of course, you know, the old adage about simplicity. It is a solar cell, and it's designed to just have what we call plug and play. So we deposit a thin, and thin means less than 1 micron thick layer of this perovskite material on top of an ordinary silicon solar cell. And those just go into ordinary solar modules. So when you're finished, you have a module that looks same size, same color, same shape as an ordinary silicon module, but it actually is, of course, 20% more efficient than any module you can buy to get today. So, you know, we started back in 2010 as a spin out of the University of Oxford, co-founded by Henry Snaith. I joined in 2014, 7 years ago, and as George said, met him on my first day. And we revised our product approach, which was originally designed to produce pieces of glass to go into buildings that could produce energy from the glass. It was a great idea, but it's kind of a niche marketplace, and it's a very difficult thing to execute. And we moved to this concept of a tandem solar cell that described that, of course, is much easier to be adopted by the industry, and 95% of this industry is based on silicon. So we have 2 sites, a headquarters and R&D site in the UK, in Yarnton. We moved for our original site in Brandenburg with about 50 staff, and pilot manufacturing line in Germany at the upper right with about 70 people. We've raised 115 million pounds to date through Series D, with the last close in mid-2019. But remember, our origins are pure Oxfordshire, with support from investors in the Oxford area, including OTIF at the time, George's fund, the university, and other friends. And so we would not be here without those sort of initial believers. And I hope we're going to be able to claim, as George is hinting at, that we're a success story. And congratulations to OIC for, you know, the recent IPO and Immunocore. So that's, I'm sure, very exciting. So faster, faster, faster. So we've been moving very rapidly, by the way, because we don't believe in this typical linear process of R&D, followed by a pilot line, followed by production line, but we actually begin each phase of before the next phase is done. It's riskier, but it's much faster. And try it. It's the only approach I believe in. And 7 years is actually a very speedy transition from concept to commercialization for a PV technology that traditionally takes decades to change. So let's take a look at what progress we've made since this 2019 Series D. Well, we ordered equipment to produce tandem solar cells, our product, in a manufacturing line in our Brandenburg, Germany facility. We've set a new world record, so we have the most efficient solar cell in the world. We've made our solar cells in modules and had them tested and certified by third parties for both performance and reliability. And despite COVID, in managing some facility and equipment delays, we're nearly ready to start up this factory and production line for ramping later this year in Germany. So this is a satellite image of our site in Germany over on the left. It was a former solar panel manufacturing facility owned by Bosch Solar, and we bought it for about 5% of its original cost, which is a really effective way to do things. Don't put it to the bricks and mortar, and repurposed it into first a pilot line, and now it's our manufacturing facility. And although the capacity is only 100 megawatts, which is pretty small by today's standard, in that same footprint, we can actually expand it all the way up to 250 megawatts if needed. It's an attractive and well-built building, no surprise, and it's a German construction. So here's just a peek inside that factory. I'm not sure if the video plays, but it's just a short image what it looks like. And look, the floors are so shiny, and it's a beautiful building. It's about 100 kilometers west of Berlin, and it's got about 17,000 square meters gross space. And even, it's no surprise, Elon Musk chose to locate his new factory not far away outside Berlin also. So this is just our first step. We call it the 100 megawatt line, our mega scale. The solar cells that we produce will be supplied to European module partners for use in residential rooftop applications. And then beyond that, of course, we intend to scale this to the gigawatt level because, of course, the residential applications are of a smaller volume. But in the residential rooftop application, actually the higher power density is most important because you have a fixed amount of space. So if you can put more power in that rooftop, that's what the customers want to pay for. That's part of the unique selling factor of these high efficiency solar cells first. And of course, those customers are willing to pay the most and therefore generate the highest margins. But we want to scale beyond that. We want to address the commercial market and the utility market going forward. And of course, that requires us to scale our factory to much larger sizes, at least a gigawatt in size with capacity expansions. So if you look at the potential for this product, you get very strong growth in the EBITDA margin when you scale these factories up at the gigawatt level, and that we expect to be able to do beginning in 2024 with first gigawatt revenues coming out of 2025. Now, we're not going to make the bottom silicon solar cells anymore at the gigawatt scale, because at that point, these are a commodity, and our, of course, expertise is in the perovskite part of the solar cell. And that's the part we're going to make in these gigawatt factories. And you can see when you scale to these large scale expansions, this on the left is the expansion capacity, and by the end of the decade we'll have more than 10 gigawatts of capacity, and that's to address the multi-terawatt market. Remember, by 2050 we need 14 terawatts of PV, so that's like 1,000 gigawatt scale factories. So there's definitely $6 trillion worth of business out there. And as you ramp, you get substantial, revenue from this factory. And of course, there's a sustainability benefit too. When you do something like this, is you don't have as much glass that you have to ship around the world. So our solar cells begin at an efficiency beyond what silicon has ever achieved and beyond its theoretical limitation at 27%, but that is just the beginning. We have a roadmap that takes those solar cells to even higher efficiency. So going forward, our product actually will become even more cost efficient from the energy that it generates. So here's a summary of our transition planning on what we do. We'll maintain our UK site up the road. This is our 100 megawatt, our R&D facility where we generate the new technology. We'll have our factory in Germany at the 100 megawatt scale, and we'll be going after our gigawatt factory somewhere in Europe is the expectation. We've had strong support from both of our strategic and institutional investors to date, but we have begun a Series E funding round. And so this is being managed by our financial advisor, Credit Suisse. We expect to raise at least 100 million pounds, which we'll use to fund the planning and initial stages for the gigawatt factory. We may be actually raise as much as 200 million pounds, which would fully fund the first gigawatt plants. And I should note that beginning next year, the German plant will actually be cash positive, even at the limited volumes. But of course, we still have to fund our R&D, et cetera. This will be our last funding round before an expected IPO or other exit event. So, Bloomberg is saying that PV is already cheap, and in a few years it will be the cheapest form of energy. So if you look at these people who forecast future technologies, just ignore them. They don't understand it. Don't listen to those kinds of gloomy forecasts. Look at what we can do. By making this perovskite solar cell, we potentially, which is our mission, to make perovskite mainstream, we can accelerate the adoption of solar. And so the future is all electric.
Thanks, Chris. And that's it from us. Looking forward, we will be looking to see how we can make future editions of these more interactive, and we'll be looking for your feedback on how we can do these better. Please drop us a comment below and like and subscribe if you enjoyed it. Thanks for joining us. I've been Gregg Brown for Oxford University Innovation, and I'll see you next time.